Okay, hello everyone. Welcome to this presentation and welcome to the 11th International Conference on Soft Computing for Problem Solving, SocProS 2020. And this event is held in the Indian Institute of Technology, Mandi, Himachal Pradesh, India. Well, welcome to this very specific presentation, and the title is Power Converter Dominated System, Challenges and Solutions. And before I start, I would like to introduce myself. My name is Francisco Gonzalez-Longatt. I am a full professor at the University of Southeastern Norway and also the founder and leader of the DGenSys lab. DGenSys is basically the short for Digital Energy System Laboratory. It's basically a real-time hardware-in-the-loop laboratory facility built for research. And if you want to know more about this, I highly suggest to visit the website fglongatt.org. Well, but it's time to start this amazing presentation. And before I start, I usually present some motivation. What is the reason that I am talking about challenges and solutions for power converter dominated systems? And the best way that I found to introduce this kind of situation is basically using this very famous photo. I believe many of you know this photo. This photo is basically a photo taken in 1900s in United States of America. Specifically, we are talking about the Fifth Avenue, the famous Fifth Avenue in New York City. And this photo is basically taken on a Sunday, Easter Sunday in 1900. And as you can see, there are many people walking around, but also you can see that there are many vehicles on the road. And now probably you are wondering, where is the car? Because if you realize the majority of the vehicles here, they are basically horse carriage. But there is only one car in that very specific photo. But now I would like to show the same scene, but 13 years later. 13 years later, in 1913, this is again the same location. We are talking about the famous Fifth Avenue in New York City, in United States of America. And even is almost the same date. We are talking about the Sunday Easter on 1913. But now you are wondering, where is the horse carriage? And this photo is quite dramatic because you can see a massive change related to transportation in only 13 years, 13 years. And the reason here is that you can see how we move from one technology, that is the horse carriage, to a car that is basically moved by the internal combustion engine. And what is reality is that this new technology, internal combustion engines, they replace the horses. And it's very interesting because Henry Ford, this amazing businessman, American businessman, Henry Ford one time was asked about this radical change created by the internal combustion. And he said, if I had listened in the masses, all they wanted was a faster car. And to be honest, the 20th century has been dominated until a few years ago by the internal combustion engine, a technology that started around 1900s. Because if you look the technology, Henry Ford started the use of internal combustion engine in July 1903. And that was the starting point of this dramatic technology disruption. But probably you are seated over there thinking about why. What is the reason that this gentleman that's supposed to be talking about power converters is talking about cars, a horse carriage? And the reason is very simple, because now I can use the same photo. And I can ask you, in this case, where is the synchronous generator? And the situation is extremely simple. The situation is that we are changing the way that we are producing electricity, the way that we are consuming electricity, the way that we are transmitting the electricity. And this is basically a technological change that is right now happening in many countries around the world. And the question is, where is the synchronous generator? And the synchronous generator is a technology that has been for more than a century in electrical power system. But today, the behavior of those synchronous generators start to be challenged by a new technology that received the name power electronic converters. And you can see over there that there is a single synchronous generator in this amazing photo, where the majority of the technologies, the production and consumption, are using power electronic converters. But now, what is the agenda? The agenda for today is extremely simple. I will start with a short description about the path to net zero. We are moving to reduce the carbon emissions to reaching net zero, and even some countries, they are thinking about negative carbon emissions. But we will discuss a bit that later. Then we will talk about the paths that we need to do in this transition to net zero. And that discussion will be related with electrical power system, because they have the most important or the key role inside the decarbonization of the energy sector. And then I will answer the question, what is the issue with power electronic converters? What is the problem related with the penetration of power electronic converters? Then I will discuss with you some of the possible solutions that we are developing right now regarding and making a stable and secure power electronic dominated electrical system. Then I will go across a short overview about inverter-based resources, type of inverters, controllers, and so on, and some closing remarks, okay? Well, let's start this presentation. Let's start with this discussion, why we are moving to the net zero. And the reality is that the climate change is a full reality. You can see many evidence worldwide about the consequence of the CO2 emissions at the atmosphere. And right now, there is an immense pressure to reduce the CO2 emissions, because right now we are in what we call a climate emergency. The glaciers are melting down, the ocean is increasing on height, and we are receiving the consequence of the global warming. Now, what is interesting is that many countries around the world, they have been committed in order to reduce these CO2 emissions. And there are many countries that they are already having targets in legal form that they engage for the net zero position. And in this slide, you can see that there are already several countries around the world that they are already in the net zero. That is the beautiful case. That is the beautiful case, for instance, of Suriname and Bhutan. Of course, those countries, they have many hydraulic resources, hydropower resources to produce electricity. But there are many other countries, especially in Europe, like Germany, Sweden, United Kingdom, France, that they are already committed and engaged in law to reach the net zero emission. For instance, Germany is already committed for 2045, Sweden 2025, and my favorite case, the United Kingdom, is committed to 2050. However, that is the legal document, but there are already places in the United Kingdom that they are already engaged to reach the net zero. Beautiful and large metropolitan cities like Glasgow, they are already committed for 2030. Manchester, the beautiful city, is committed to reach the net zero for 2038. And even in the south of England, Bristol is already committed for 2030. And of course, there are many other countries worldwide that they have committed, but they are basically in a proposed legislation. If you want to see more details about this, I highly suggest that you go here to this link at the bottom, and you can see the Energy and Climate Intelligence Unit. And over there, you can get more information about this tracker, about the work net zero tracker around the world, okay? But what is interesting is that many countries are committed, but there is already a path defined for reaching the net zero emission by 2050. If you go and look into this amazing document from the International Energy Agency, they define the path for net zero for 2050. The document that is titled A Roadmap for the Global Energy Sector is defining the path for the electricity and heat, the industry, the transport, the buildings, and other sectors in order to reach the net zero for 2050. And what is interesting for us is that, for instance, you can see here at the slide, by 2030, 1,020 gigawatts annual solar and wind power will be added to the generation mix. And what is very interesting is for 2035, overall net zero emission electricity will be reached for the most developed economies. And for 2040, the net zero emissions is supposed to be reached globally for the electricity sector. By 2050, we are expecting around 70% of the electricity generation coming from renewable resources like the solar photovoltaic or solar PV and wind power. If you want to read more about this, I highly suggest that you go to the website of the International Energy Agency and please read this very important report. But what is important for us is how can we reach that net zero? But also, what are the consequences? What are the main challenges coming from reaching that net zero for the electricity sector? And in this slide, I would like to show you the most important aspect that we need to take into consideration when we are talking about the electricity sector. What is interesting for us is that we are changing in many ways the electricity sector. For instance, production. We are moving from very large centralized power plants with a lot of inertia, but using a very no environmentally friendly technologies. We are decommissioning coal power plants, oil power plants, and we are expecting to decommission all those very old technologies that they pollute the environment and they don't contribute with the CO2 reduction. And instead of them, we are installing many small size renewable generation like the wind power and also the PV system. And what is important is that one element that is playing a very important role in this transition is the battery energy storage. Because as you must be aware, all those environmentally friendly technologies, they are highly variable because the primary energy resource. In the wind power, of course, the wind speed can change time to time. From the PV system, of course, we have the clouds, and the PV power production can change. For that reason, battery energy storage is a key enabler in order to reach the 100% of renewables in the electrical power system, but at the same time, the net zero. On the other side, we have the customers. The customer has been for many years just a passive element inside the electricity sector. They have been consuming electricity and nothing more than that. They only pay for the electricity, for the kilowatts hour that they consume. However, that paradigm is changing. Right now, the customer is transforming the way that they are using the electricity. Right now, the customer is more active. They are participating in the system because right now, there are many customers that they have PV solar panel at the roof. As a consequence, they can have very distributed and highly variable but local generation. But at the same time, there are new technologies. There are new technologies coming to the market, like the electric vehicle, like the heat pumps, like the small size battery energy storage. And as a consequence, the customer is not again the same passive element inside the electrical power system. Right now, we have customers that they are producing electricity, and the legislation is allowing them to receive payment for that electricity. That means that the customer stopped to be passive component, and right now we use the name prosumer. Prosumer is a customer that has the possibility of selling electricity to the system. But if the customer is providing electricity to the electricity grid, of course the distribution system must change from that classical one-directional power flow from the top to the bottom. And right now we are having two-way power flows inside the distribution system. Right now we are using what we call the active distribution system because the distribution system is changing dynamically, and that is a huge change for the distribution system. At the transmission level also, we are having many challenges because those very large power lines going from very long distances, that they move bulk power, they are starting to be substitute for smaller power lines with a varied kind of topologies and interconnections. But what is most important is that the technologies of battery is enable the possibility that we install this battery energy storage at transmission level. We are talking about a utility size battery energy storage. We are talking about several hundred megawatts and also for several hours. That means we are talking about huge battery energy storage. And of course, with the changes that we are having in production and consumption, the market is also changing. In the past, we used to have a very centralized market, a very national market, and in that market, we were dealing only about energy. Kilowatts hour or megawatts hour. But the reason now is that if the customer is starting to produce electricity and we need to pay compensation to them and some tariff, of course now we have more regional control. We have a market that is not only energy, and we are talking about decentralizing and ignoring boundaries in this power production, transmission, distribution, and consumption. What I'm telling you is that now the market is changing to allow a smaller generation unit to be part of these balancing services, to be active part in the production of electricity, and that is extremely exciting. Finally, to close this explanation, what I can tell you is that the way that we are designing and operating electrical power system must change. Because we need to pass from that very old paradigm when we were only human-based operation, that we were extremely dependent on forecast and we react to the changes in the electrical power system. As renewable start to be a high component of the generation mix, we need to change the way that we are operating the system. Because right now, with very small generators, we have thousands of many or more of them inside the electrical power system. The decision taken cannot be a human-based process. For that reason, we are taking the advantages of the new technologies like machine learning, like artificial intelligence, in order to take the decision. But also we are taking the advantages of the very fast computational power, and as a consequence we are moving to real-time calculation, real-time decisions using distributed computing power across all the system. And also one very interesting point is that we are going further, because the classical operation was a situation of the main or the big market that was national, and then we react to the changes on the distribution level. But right now we need to take into consideration and take the advantages that the prosumer can provide to us. Well, as you can see, there are many beautiful challenges. And I highly suggest, if you want to learn more about this, I highly suggest that you go to the Institute for Energy, Economic and Financial Analysis. This institute provides, in the case of Australia, some paths related to those changes related to the electricity sector. But now, why I am talking about power converter dominated systems? Because the reality is that as we are changing the way that we are producing electricity, and you can see over there that the future will be more renewable, like solar PV plants, large wind farms, and hydropower. Well, but also we will start to have very small distributed generation, solar PV at the roof of many houses, and also small and decentralized battery energy storage, some of them located at the demand side. But also some embedded technologies like the electric vehicles. At transmission level, of course, we will have utility-scale battery energy storage. What I am trying to tell you is that now the way that the power system is created and is operated is changing. And if you look this beautiful slide, you will see that here we have power converter, over here, over there, there, and I can keep counting here. And if you remember my very first introduction, I say, where is the synchronous generator? Because right now the situation is the amount of penetration of these technologies that they are using the power converter as interface. If you want to read more about this change on the paradigm, I highly suggest that you go and read my book, Modeling and Simulation of Power Electronic Converter Power Systems in Power Factory, okay? But many people believe that this very specific slide that I am showing here is just inside my mind and it's just a dream. But to be honest, this is not a dream. Depending on the country that you are located, the local reality is very different. And today I would like to bring your attention to one of my favorite countries around the world, and that is Australia. In this slide, I am showing you what is one of the most important reports coming from the Australian Energy Market Operator, AEMO. In March 2021, they published a report that is called the Engineering Framework. And in this engineering framework, this plot that you have in front of you appear. And what is interesting is that this plot shows the changes of half-hourly wind power generation and solar generation compared with the synchronous generator. What I'm telling you is that here you can see on the horizontal axis, I am presenting in gigawatts the IBR generation. IBR is the short name of inverter-based generation. I mean just wind power and solar power. And in the vertical axis over here, you can see synchronous generation. And we are talking again about gigawatts. But what is important in this very interesting plot? That using three different colors, you can see year 2018, 2019, and 2020. And as you can see, they are very high penetration of solar and wind power. As you can see, the maximum level rise from 38% in 2018 to 47% in 2019. And what is surprising is in 2020, this level reached 52%. And 52% is a very important number, because 52% of generation coming from power converters means that power converters were the majority of the technology used for power production. And what is relevant for me in this very specific presentation is that 52% penetration of power converters mean that the synchronous generator was a minority. And that is true because the synchronous generation decreased from 13.7 gigawatts in 2018 to 10.8 gigawatts in 2020. What I am trying to tell you is that Australia, at least, they are in the situation of a power converter dominated system, and that create massive challenges that right now I will discuss with all of you. Many of you are wondering, okay, we are disconnecting synchronous generator, we are installing so many power converter, but what is the problem? What is the issue with this massive power converter penetration? Well, as I presented in my previous slide, what is happening in many power systems around the world, like the case of Australia, the case of Great Britain, the case of United States, specifically Texas, is that we are disconnecting many non-environmentally friendly power generation power plants. And those power plants, they are based on synchronous generators. If you look this very specific slide, you can see that we are reducing the number of synchronous generators and we are increasing the number of power converters. For instance, I highlight here the case of Australia. In 2020, 48% penetration of synchronous generator and high 52% power converters. But now, what I can tell you is that some countries are moving in this tendency, and you will see many countries increasing more and more the penetration of power electronic converters. Probably you are sitting over there wondering, Professor, but it's possible that we reach 100% inverter-based resources. And that is the ideal case, 100% of inverter-based resources. But what I can tell you is the following. This is no utopic. This is no a dream. 100% power converter has been a reality in other systems. For instance, microgrids. There are many microgrids around the world that they are already 100% inverter-based resources. And also some kind of transportation chips that they are already using inverter-based resources. What I can tell you is that the challenge is for huge interconnected power system. But probably you can ask me, Professor, do you think that the continental Europe will reach 100% inverter? And I must tell you, probably not in my time scale, I will see 100% penetration of power converter in continental Europe. And the reason is simple, because there's still many good technologies, generation technologies, that they still using synchronous generators. And as a consequence, I don't see them disappearing in short term in classical and huge continental Europe. What I can tell you, for instance, is that nuclear power plant in the case of France, in the case of some other European countries, I don't see them disappearing in my lifetime, okay? However, depending on the country that you are located, this reality can be faster or can be slower. But now, what is the issue? Well, the issue, I love to use this very interesting slide over here. In this slide, I would like to tell you that the situation is that we are decreasing the amount of synchronous generators. And decreasing the number of synchronous generators means that we are installing more and more high power converters. And the issue is not because we are installing more power converters. The issue is related with the thing that they are extremely different to the synchronous machine. To be honest, a power converter is dramatically different to the beautiful classical synchronous machine. And the problem is that power engineers, we are confusing them. I present here two animals. I love those animals. On the left-hand side, you can see this four-legged animal. This is the Equus Firus Caballus. That is Latin for horse. And on the right-hand side, you can see the Equus Quagga. That is the Latin for zebra. Zebra and horses, they look similar. They have four legs, they have a tail, they have two ears, they have two eyes, they have a nose. They look similar. But this beautiful guy on the right-hand side, they have white and black stripes. And they look similar, but they behave extremely, extremely different. What I want that you take as a takeaway from this presentation is that the power converter is dramatically different to the synchronous machine. And what is the reason for that? Well, in this slide, you can see the two very interesting things. The synchronous machine is extremely simple. It's an electromechanical conversion device. It's an electromechanical conversion device. You apply mechanical power on one side, the shaft, and you get electricity on the other side. For that reason, receive the name of electromechanical conversion. And all the conversion is happening inside the rotating machine and basically using properties of electromagnetism. From the control point of view is very simple because you have at least two control loops, one for frequency and one for AC voltage, okay? It's extremely simple. But what is extremely important that all of you understand is that the synchronous machine has been for more than 100 years in the electrical power system providing services. Some of those services, even we power engineers, we complain about those services. For instance, short circuit currents. Short circuit currents few decades ago start to be a problem, and we were complaining about short circuit currents because the synchronous machine is able to be overloaded and produce high current, high fault currents. And that is an additional overcurrent that is possible because the machine has the possibility of dissipating this amount of energy. For instance, also, the synchronous machine has a rotating component that receives the name rotor. And this rotor has a beautiful electromechanical physical property that is called rotational inertia. And the rotational inertia is amazing and is helping us because provide the possibility that in a steady-state operation, during normal operation, and also during disturbances, they allow to minimize or to reduce the frequency deviation. And that has been a service that not much people noticed until a couple decades ago. Frequency control is extremely simple in the synchronous machine because the synchronous machine doesn't require so many sensors, digital processing signal, and so on. And also the system strength. Well, system strength is a very interesting concept that we have started to look at very carefully probably 5 or 6 years ago. Because the synchronous machine always produces a beautiful sine wave that we can use inside the electrical power system. And we didn't consider the possibility that that signal start to be disturbed and start to be also lacking of the sine wave shape. Well, what I want to tell you from this slide is that the synchronous machine has been providing services for many years. And because we are using dispatchable technologies as primary resources, to be honest, the control and the operation of the electrical power system has been extremely simple. But right now, I would like to tell you about the power converter. The power converter is not similar to the synchronous machine. It's delivering electrical power. Yes, it's delivering electrical power. But the way that this device works is extremely different. Because the power converter is using very small size semiconductor devices to do what we call commutation. And those very small semiconductor devices, they are extremely sensible. And that is the reason that when we think about the services coming from the synchronous machine, there are many services that we cannot provide with the power converter. Because the power converter has no overloading capacity. And if we include overloading capacity, that requires a lot of money. For that reason, the power converter is lacking of the possibility of providing the same services. On the other hand, the power converter has no energy storage capability. You can add energy storage like battery on the DC side, but it's not inside the converter. Inside the converter, what we have is ideal switches commutating and converting the electricity, no more than that. Another thing is that the power converter requires many control loops. It's very different to the synchronous machine, require measurements, require processing, in this case digital processing, and the kind of controls that we require for those power converters, they must be extremely fast. What I can tell you is that from those power converters, we want to have many services, like services coming from synchronization and rotor angle stability. Frequency regulation is one of the services that we have been already using from power converters and also voltage regulation. Many of the grid codes around the world, they are already including frequency regulation and voltage regulation. And also, if you look the IEEE 1547, you can see that this is a capability already asked for what we call the smart inverters. Damping oscillation is a possibility that can be enabled in these power converters. In fact, some of the grid code requirements in the UK already establish some requirement for damping oscillations. However, providing those services makes several challenges. Several challenges because, for instance, the capacity of those power converters is still increasing and depend basically on the size of these very small commutation devices. Also, the energy that is required must come from one primary energy resource, and that primary energy resource, of course, has many possibilities, but at the same time has so many restrictions. I will not go full details over here, but you must understand that the PV and also the wind power, they have restrictions regarding the situation of the primary energy resources changing. And there are many other limitations related with the inverter. For instance, if you are using the old technology that we call the grid following converter, the grid following converter requires a synchronous mechanism. And this synchronization mechanism is attached to what we call the phase lock. And the phase lock has been around for many decades. However, it's a technology that has some limitations. Also, there are limitations regarding the models because they are not a standardization at the moment. We are working in several working groups related to the IEEE, defining some of the main services and characteristics of those power converters, but there are many work to do, especially regarding the power system dynamic model. Right now, what we have is a manufacturer-dependent modeling, and also in the form of black box. Okay? Well, but in order to move forward, we need to answer the question, okay, and what is the issue? Well, the issue is that we are losing the very beautiful properties coming from the synchronous generators, and we are having those very fragile components, the power converters. And well, in this sense, we need to define a new way to develop and to create the electrical power system. And it's time to discuss, okay, how can we develop a stable and secure power electronic dominated grid? And here in this slide that you will see in many of my presentations, I would like to show you the mechanism that we can follow in order to enhance the power system stability. And we can classify, or we can include the solutions in two big groups: the short-term solutions and the long-term solutions. The short-term solutions, there are many of them that we have been working for probably more than 1 decade. For instance, grid code connections. The grid code is the document created by many utilities and organizations around the world in order to define the minimum requirements for safety and secure operation of the system from the components that we are connecting. And many grid codes around the world have been evolved and have been adapting to this new power converter dominated situation. For instance, IEEE has created many standards, and this standard, for instance, the 1547, have evolved in the time. Starting in 2014, 2015, around those years, this standard have evolved until right now we have the smart inverter. The smart inverter is a power converter that now can provide functionalities to be friendly to the grid. And what I can tell you is that many other countries around the world, they already create or open the possibility of including more power converters in the grid code. For instance, in the UK, we are already defining the minimum characteristic of the grid forming converters inside the grid forming. Okay? In other countries, we have been using what we call auxiliary services. Ancillary services, there are many kinds of services, but for instance, one of the most important services that has been starting to be more and more attractive as the penetration of power converter increase is the inertia. And for that reason, in some countries, they already start to ask frequency response, primary frequency response from the power converters. And more specifically, in some countries, they are already asking for the inertia response from power converters, and that is auxiliary services. In some other countries, we already define that we need to take some short-term solution. For instance, in the case of the UK, the short-circuit currents are decreasing quite fast. And one very simple way to produce short-circuit contribution is using what we call the synchronous condenser. The synchronous condenser is a synchronous machine that is working to deliver reactive power, but during a short circuit, they have the possibility of contributing with a short-circuit currents. And short-circuit currents are extremely important when we are talking about protections, specifically for overcurrent protection, detection, and location. And finally, some other countries, they are using what we call mitigation measures. And I will not go in details in this presentation because we are running out the time, but I would like to discuss some of the most important long-term solutions. Many countries around the world has been looking to enable primary frequency response in power converters. Primary frequency response can be enabled on them. However, what is very important that you must understand is that the power converter has not overloading capacity. It's not similar to the synchronous machine. For that reason, this synthetic inertia or digital inertia or emulated inertia, there are many names in the market, many flavors about this kind of, let's say, controller. Synthetic inertia has the limitation that require the value of that gain on that controller to be very careful specified. For that reason, the other possible solution for solving the problems related with power electronic dominated systems is, of course, using the converter. The converter, many people say that they are the problem. In opinion of me, I would like to say that the grid forming, the grid power converter is probably the solution that we are looking for. What we need to understand is that the power converter is extremely fast. They have the possibility to be even faster than the synchronous machine. And one of the paradigms that we are using recently to try to solve the problem of the, let's say, power electronic converters dominated system is using what we call the grid forming. The grid forming is a new control technique that basically is replicating the behavior of the synchronous machine. However, there are two very important characteristics that I would like to say regarding grid forming. The first one is that the model of the grid forming control can be in a circuit that is basically a voltage behind impedance. For that reason, this model is more replicating the behavior of that real synchronous machine. And second, because we are not using the classical synchronization mechanism based on PLL, this kind of synchronization is based on angle or based on power. As a consequence, these kind of converters with this kind of technology, they are more stable and they are adding more stability to the electrical power system. Well, we are reaching the end of this presentation, and it's really sad that we are running out the time, but it's time to make some conclusions here. And to be honest, some takeaway. And at this moment, there are many things that I would like to say, but I think the most important conclusion of this presentation is that you understand that the electrical power systems, they are changing. The electric industry is changing. And we need to change also the way that we are thinking, the way that we are developing, planning, and operating the electrical systems. Because now we are disconnecting many of those synchronous machines, and we are connecting more of those power converters. But in this photo, I would like to take this photo as the final message for this presentation. Because as you can see over here, I have a horse, but I am trying to put on them a costume that is looking like a zebra. And that is my main takeaway here, that probably we are trying to make the power converter to look like a synchronous machine. It's my opinion, my personal opinion, that we need to take the advantages offering these kind of power converters. If we are reaching penetration levels of 52% like the case of Australia, why do we need to keep thinking and developing and operating the electrical power system when the center is not longer the synchronous machine? What I'm telling you is that probably we need to start to forget the synchronous machine paradigm and focus on developing, planning, and operating mechanism to take the advantages of those very fast and very beautiful power converters. Well, this is basically my message in this presentation, and this is the end of my presentation here, Power Converter Dominated System Challenges and Solutions. It was a pleasure having all of you and be here at the 11th International Conference on Soft Computing and Problem Solving. And for me, it's very, very important for me be in this conference, because it's at the Indian Institute of Technology, Mandi, and I have very good memories of my time in Mandi, and also my very good friend is over there, Professor Baratsai. Well, it's time for starting some questions, and I am here to try to answer your question. Thank you very much for watching.